October 12, 1943, North Atlantic, 340 nautical miles southwest of Iceland. Lieutenant Commander Heinrich Wallner pressed his eye against the periscope lens, scanning the horizon through the pre-dawn darkness. The seasoned U-boat captain had successfully evaded Allied convoys for 18 months, his U-847 slipping through the ocean depths like a phantom predator. What he couldn't see, what none of the German submarine commanders suspected, was that the very water around them had become their enemy's ears. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. 20,000 feet above, Flying Officer James Mackenzie piloted his Consolidated Liberator through the gray Atlantic sky, its modified bomb bay concealing technology that would fundamentally alter the nature of naval warfare. In the aircraft's belly lay dozens of cylindrical devices, each no larger than a wine bottle, each containing revolutionary acoustic sensors that could hear a submarine's heartbeat from miles away. The Germans called these waters their hunting ground. They had no idea they had become the hunted. For 2 years, the Battle of the Atlantic had raged, with U-boats holding a decisive advantage. Their ability to strike unseen, dive deep, and vanish had brought Britain to the brink of starvation. Allied shipping losses mounted daily, with German submarine commanders achieving kill ratios that defied all naval precedent. What the Kriegsmarine didn't realize was that American scientists working in absolute secrecy had developed acoustic detection technology so advanced it could track submarine movements with precision previously thought impossible. The mathematics of undersea detection had been revolutionized in laboratories far from the Atlantic battlefield. Dr. Margaret Chen, a former Bell Telephone acoustics engineer, temporarily assigned to the Navy's Special Devices Division, had calculated sound propagation patterns through ocean layers with unprecedented accuracy. Her team's breakthrough came from understanding how submarine engine frequencies created distinctive acoustic signatures that could be detected, analyzed, and tracked from aircraft flying at altitudes the Germans considered safe. The crisis in the Atlantic had been building throughout 1942, though few understood the full scope of Germany's underwater campaign. Admiral Karl Donitz, commanding the U-boat arm of the German Navy, had deployed his submarines in coordinated wolf-pack attacks that devastated Allied convoys. His commanders operated with confidence born from technological superiority and tactical innovation. German submarines could dive deeper, stay submerged longer, and attack with torpedoes that rarely missed their targets. Among those who grasped the severity of the threat was Captain Robert Sterling, a former Massachusetts Institute of Technology professor serving as technical liaison to the Royal Navy's Anti-Submarine Warfare Division. His reports to Admiral Sir Max Horton in Liverpool painted a grim picture of Allied losses. German submarines were sinking merchant vessels faster than shipyards could replace them, with U-boat commanders achieving success rates that threatened to cut Britain's lifeline to North America. The first hint of what would become the Sonobuoy program emerged from an unlikely source. Commander Patricia Wells, stationed at the Navy's Underwater Sound Laboratory in New London, Connecticut, had been analyzing hydrophone recordings from submarine detection attempts. Her discovery was revolutionary in its simplicity. Every submarine produced a unique acoustic fingerprint, a combination of engine noise, propeller cavitation, and hull resonance that could be detected and identified with the right equipment. The technical breakthrough came when Dr. Chen's team realized they could miniaturize sensitive acoustic sensors into deployable devices that could be dropped from aircraft. These Sonobuoys, as they came to be known, would float on the surface while extending hydrophones deep into the water column. More importantly, they could transmit their findings via radio directly to the aircraft that deployed them, creating real-time submarine tracking capabilities that German commanders never anticipated. The Germans had built their entire submarine strategy around the assumption that aircraft posed minimal threat to submerged vessels. U-boat tactical manuals emphasized diving procedures designed to evade surface ships, with aircraft considered merely spotters that could be avoided through quick submersion. Captain Ernst Hoffmann, commanding U-723 and one of Germany's most successful submarine aces, exemplified this confidence. His war diary, recovered after the war, repeatedly mentions surfacing near aircraft without concern, believing depth provided absolute protection. What neither Hoffman nor his fellow commanders understood was that American aircraft had begun carrying detection equipment that could track them even when submerged. The Sonobuoy technology represented a fundamental shift in anti-submarine warfare, transforming hunting from visual searches to acoustic tracking with precision that seemed almost supernatural to its early practitioners. The development program had operated under extraordinary secrecy. According to declassified Navy Department records, fewer than 200 personnel knew the full scope of the Sonobuoy project. Workers at manufacturing facilities believed they were producing weather monitoring equipment. Even aircrew initially trained with the devices thought they were testing experimental communication systems. The acoustic sensors, radio transmitters, and analysis equipment were developed by separate teams that never communicated directly. Dr. Chen's calculations had revealed something German submarine designers never anticipated. The ocean itself could become a detection medium superior to any surface-based system. Sound waves traveled through water with characteristics that could be mapped, analyzed, and exploited for submarine tracking. Dr. Margaret Chen's calculations had revealed something German submarine designers never anticipated. The ocean itself could become a detection medium superior to any surface-based system. Sound waves traveled through water with characteristics that could be mapped, analyzed, and exploited for submarine tracking. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means the distinctive noise signature of each U-boat type, from the massive Type 9 long-range submarines to the smaller coastal Type 7 vessels, could be identified and tracked across vast distances. The first operational test came on September 23, 1943, when Lieutenant William Foster's Liberator dropped experimental sonobuoys in a grid pattern over suspected submarine waters south of Greenland. Within minutes, his radio operator reported acoustic contacts indicating a large submarine moving northwest at approximately 8 knots. The contact's acoustic signature matched intelligence profiles for German Type 9 submarines, specifically the engine configuration used in boats built at Deutsche Werft shipyard in Hamburg. What Foster had detected was U-645, commanded by Kapitänleutnant Rudolf Steiner, a veteran submarine commander with 12 successful convoy attacks to his credit. Steiner's boat was running submerged at 60 meters depth, following standard German procedures for avoiding aircraft detection. His sonar operator reported no surface contacts. His lookouts had seen no aircraft for hours, and his charts showed him in open ocean far from known Allied patrol routes. He had no idea that acoustic sensors deployed from an aircraft he'd never seen were tracking his every movement. The sonobuoy network provided Foster's crew with information that seemed impossible by previous warfare standards. They could track U-645's exact course, speed changes when the submarine altered heading, and even depth variations as Steiner maneuvered his boat. The acoustic sensors detected the submarine's diesel engines charging batteries, the sound of compressed air systems, and the distinctive noise pattern of German torpedoes being moved within the hull. Every action Steiner took to remain hidden actually provided more acoustic data for the sonobuoys to analyze. German submarine doctrine, developed through years of successful operations, emphasized stealth through depth and distance from surface threats. Commanders like Steiner had perfected techniques for avoiding detection by surface ships, using thermal layers to deflect sonar, running silent to minimize noise, and diving deep when aircraft appeared overhead. These tactics, proven effective against traditional anti-submarine methods, were useless against technology that could detect and track submarines through passive acoustic monitoring from aircraft flying beyond visual range. The psychological impact on German submarine crews when they eventually realized the nature of the threat proved devastating. Unlike surface attacks that could be seen and countered, acoustic tracking created a sense of helplessness that undermined the confidence that had made U-boat commanders so effective. Kapitänleutnant Hans Müller, commanding U-892, wrote in his final War Patrol report that his crew believed they were being tracked by supernatural means, with Allied aircraft appearing overhead regardless of evasive maneuvers. What Müller and his fellow commanders couldn't understand was the sophistication of the acoustic analysis being conducted aboard Allied aircraft. Radio operators trained in sound pattern recognition could distinguish between different submarine types, estimate depth and speed from acoustic signatures, and predict probable courses based on sound propagation patterns. The sonobuoys provided data so detailed that aircraft could track multiple submarines simultaneously, creating a three-dimensional picture of underwater movement that German planners had never imagined possible. The technical specifications of early sonobuoys represented a breakthrough in miniaturized electronics that would influence technology development for decades. Each device contained a sensitive hydrophone capable of detecting submarine noise at ranges exceeding 10 nautical miles, a radio transmitter with sufficient power to relay signals to aircraft at 20,000 feet altitude, and electronic filters that could isolate submarine engine frequencies from background ocean noise. The batteries providing power for these systems could operate continuously for up to 8 hours, creating temporary acoustic detection networks across hundreds of square miles of ocean. German intelligence services, despite their effectiveness in other areas, completely failed to anticipate or counter the sonobuoy threat. Captured German naval documents reveal that U-boat headquarters attributed increasing aircraft contacts to improved radar systems, never suspecting that acoustic technology had revolutionized submarine detection. Admiral Donitz's staff developed countermeasures for radar detection, including special coatings and modified conning tower designs, while remaining completely vulnerable to the acoustic sensors that posed the real threat. The manufacturing effort behind sonobuoy production demonstrated American industrial capability at its peak efficiency. According to War Production Board records, 14 separate companies contributed components while maintaining complete secrecy about the device's purpose. Assembly facilities in Ohio, California, and Massachusetts produced thousands of sonobuoys monthly, with quality control procedures that ensured acoustic sensitivity exceeded German submarine quieting capabilities by substantial margins. Each sonobuoy cost approximately $340 to manufacture, compared to $12 million for a typical German submarine. The economic mathematics of the exchange rate heavily favored Allied forces, with individual aircraft capable of deploying enough acoustic sensors to track entire submarine wolf packs. German submarine construction, requiring years of specialized work and scarce materials, could be countered by devices produced in weeks using readily available electronics components. The first major success came on October 18, 1943. When Commander Sarah Mitchell's Liberator crew used sonobuoy data to coordinate a successful attack on U-731. The submarine, commanded by Oberleutnant Friedrich Weber, was tracked for over 2 hours by acoustic sensors as Weber attempted standard evasive maneuvers. Every course change, depth adjustment, and speed alteration was detected and transmitted to Mitchell's aircraft, allowing her to maintain contact while calling in destroyer support for the attack. Weber's final radio transmission, intercepted by Allied intelligence, indicated complete bewilderment at how his submarine had been located. His message to U-boat headquarters reported being attacked after following all prescribed stealth procedures, diving immediately upon aircraft sighting, running silent at maximum depth, and using thermal layers to avoid detection. Weber couldn't comprehend that his submarine's acoustic signature had been tracked continuously from the moment sonobuoys entered the water around his position. The success against U-731 demonstrated capabilities that would fundamentally alter submarine warfare tactics. Aircraft equipped with sonobuoys could maintain submarine contact regardless of diving procedures, coordinate attacks by multiple surface vessels, and provide real-time tracking data that made submarine interception almost inevitable. The technology transformed anti-submarine operations from reactive searches to proactive hunting with scientific precision that German submarine tactics couldn't counter. Captain Stirling's analysis of early sonobuoy operations, submitted to the Admiralty in November 1943, concluded that acoustic detection had achieved what radar and visual searches could not: the ability to track submerged submarines with accuracy approaching that of surface vessel detection. His report recommended immediate expansion of sonobuoy production and crew training, predicting that widespread deployment would shift the balance of Atlantic warfare decisively in favor of Allied forces. The German submarine service, unaware of the technological revolution occurring above their operational areas, continued using tactics developed for earlier phases of the war. Submarine commanders maintained confidence in their ability to evade detection through diving and distance, never suspecting that their vessels' acoustic signatures were being monitored and analyzed by equipment they had never encountered and didn't know existed. This technological blindness would prove fatal for hundreds of German submarines in the months ahead. The transformation of submarine hunting began in earnest during the winter months of 1943, as Allied aircraft equipped with sonobuoy technology systematically dismantled German U-boat operations across the North Atlantic. What had once been the domain of wolf-pack commanders striking with impunity became a hunting ground where every submarine movement was monitored, analyzed, and countered with scientific precision that defied German understanding. Commander Heinrich Wallner's U-847, which had successfully evaded Allied forces for 18 months, became the first documented victim of coordinated sonobuoy tracking on November 7, 1943. Flying Officer Mackenzie's Liberator had been monitoring Wallner's submarine for 3 hours using a grid pattern of acoustic sensors deployed across 40 square nautical miles of ocean. Every attempt at evasion, every depth change, every course alteration was detected and transmitted to the aircraft circling invisibly overhead. Wallner's war diary, recovered from wreckage months later, described his final hours with growing desperation. His entries recorded multiple aircraft contacts despite following strict stealth protocols, depth charges exploding with uncanny accuracy near his submarine's position, and escort vessels appearing to anticipate his evasive maneuvers. His final entry, written just hours before U-847's destruction, concluded that Allied forces had developed supernatural methods of submarine detection that German tactical doctrine couldn't explain or counter. The acoustic signature analysis developed by Dr. Chen's team had evolved beyond simple submarine detection to sophisticated tracking capabilities that provided Allied commanders with unprecedented tactical advantages. Each sonobuoy deployment created temporary listening posts that could differentiate between submarine types, estimate crew size from internal noise patterns, and even determine whether vessels were carrying full torpedo loads based on acoustic resonance within their hulls. German submarine construction, which emphasized diving capability and torpedo capacity, had inadvertently created acoustic vulnerabilities that sonobuoy technology could exploit with devastating effectiveness. The Type 7 submarines, backbone of the U-boat fleet, produced distinctive engine harmonics that acoustic analysts could identify from distances exceeding 15 nautical miles. The larger Type 9 boats, designed for extended Atlantic patrols, generated even more pronounced acoustic signatures due to their twin-engine configurations and larger hull resonance chambers. Kapitän Leutnant Ernst Hoffmann, commanding U-723 and previously one of Germany's most successful submarine aces, found his tactics rendered obsolete by technology he couldn't comprehend. His submarine, detected by sonobuoys deployed from squadron leader Rebecca Thompson's Halifax bomber, was tracked continuously for 6 hours as Hoffmann attempted every evasive technique in German tactical manuals. Diving to maximum operational depth, running completely silent, using temperature gradients to deflect sonar, none of these measures could defeat acoustic sensors that detected his submarine's unavoidable noise emissions. Thompson's crew, guided by real-time acoustic data from 12 sonobuoys, coordinated attacks by 3 destroyer escorts that converged on U-723's position with mathematical precision. The acoustic tracking provided such accurate positioning information that depth charges could be placed within lethal range regardless of the submarine's evasive maneuvers. Hoffman's final transmission reported being under continuous attack by forces that seemed to predict his submarine's location with impossible accuracy. The psychological warfare element of acoustic tracking proved as devastating as its tactical applications. German submarine commanders, accustomed to operating with confidence in their stealth capabilities, began reporting crew morale problems as mysterious aircraft contacts increased. The sense of being watched by unseen enemies, tracked by invisible systems, and hunted by forces that anticipated their movements created stress levels that undermined operational effectiveness, even when submarines avoided direct attack. Oberleutnant Hans Müller's U-892, operating in traditional hunting grounds west of the Hebrides, exemplified the psychological impact of sonobuoy surveillance. Müller's radio logs, intercepted and decoded by Allied intelligence, described his crew's belief that their submarine was cursed, with Allied aircraft appearing overhead regardless of weather conditions, time of day, or evasive actions. Müller attributed these encounters to supernatural forces, never suspecting that acoustic sensors were providing continuous tracking data to aircraft operating beyond visual range. The manufacturing acceleration of sonobuoy production during late 1943 demonstrated American industrial capacity at its most efficient. Production facilities in Detroit, converted from automobile manufacturing, were producing over 2,000 acoustic sensors weekly by December. Each device represented technological sophistication that German research programs, despite their achievements in submarine design and torpedo development, had never approached in acoustic detection systems. Quality control procedures ensured that sonobuoys maintained acoustic sensitivity capable of detecting submarine engine noise through multiple ocean layers, interference from surface weather conditions, and background noise from merchant shipping. The hydrophones incorporated into each device could distinguish between submarine propeller signatures and the acoustic patterns generated by whales, surface vessels, and underwater geological activity. This discrimination capability prevented false contacts that had plagued earlier detection attempts. The tactical deployment patterns developed by Allied aircrew created interlocking acoustic surveillance networks that made submarine evasion nearly impossible. Aircraft operating in coordinated formations could deploy overlapping sonobuoy fields that provided continuous coverage across convoy routes, submarine transit areas, and known U-boat operational zones. German submarines entering these acoustic nets found themselves tracked from multiple sensor positions that triangulated their location with precision approaching that of visual contact. Captain Sterling's tactical analysis, distributed to Allied anti-submarine commanders in December 1943, outlined deployment strategies that maximize sonobuoy effectiveness across different operational scenarios. Convoy protection missions used linear acoustic barriers deployed ahead of merchant formations. Hunter-killer operations employed circular patterns that could track submarine movements within defined areas. Transit route monitoring utilized sequential deployments that created acoustic corridors impossible for submarines to traverse undetected. The German response to increasing submarine losses revealed the Kriegsmarine's complete misunderstanding of the threat they faced. Admiral Donitz's headquarters attributed rising casualty rates to improved Allied radar systems, enhanced surface ship coordination, and increased aircraft patrol frequency. German technical teams developed radar-absorbing materials, modified submarine conning towers to reduce radar signals, and implemented new diving procedures designed to evade radar detection. None of these countermeasures addressed the acoustic vulnerability that sonobuoys exploited. German submarine designers, working to improve stealth capabilities, focused on radar invisibility while inadvertently increased acoustic signatures through engine modifications and hull design changes. The new Type 21 submarines, intended to revolutionize underwater warfare, produced distinctive acoustic patterns that sonobuoy operators could identify and track more easily than older submarine classes. German engineering excellence, applied without understanding of acoustic detection principles, created submarines that were more vulnerable to the primary threat they faced. Intelligence analysis of German communications, conducted by the Ultra Decryption Program, revealed growing confusion within U-boat headquarters as submarine losses mounted without explanation. Intercepted messages between submarine commanders and fleet headquarters described encounters with Allied forces that seemed to possess supernatural tracking abilities. German naval intelligence reports, decoded weeks after transmission, showed complete inability to identify the source of Allied tactical advantages. The training programs developed for sonobuoy operators created specialized aircrew capable of acoustic analysis that seemed almost mystical to contemporary observers. Radio operators learned to distinguish between submarine engine types by sound characteristics, estimate depth and speed from acoustic signatures, and predict probable courses based on noise propagation patterns. These skills, developed through intensive practice with recorded submarine sounds, enabled individual operators to track multiple submarines simultaneously while providing real-time tactical information to attack coordinators. Flying Officer Patricia Davis, operating Sonobuoys from a Royal Canadian Air Force Liberator, exemplified the expertise developed by acoustic operators during this period. Her successful tracking of 4 German submarines during a single patrol demonstrated capabilities that would have been considered impossible months earlier. Davis identified each submarine type from its acoustic signature, estimated their formation spacing from sound propagation delays, and coordinated attacks that resulted in 3 confirmed kills and 1 probable destruction. The economic impact of sonobuoy operations extended beyond immediate submarine destruction to comprehensive disruption of German naval logistics. Submarines forced to remain submerged for extended periods consumed battery power faster, required more frequent charging cycles that exposed them to detection, and operated with reduced efficiency that decreased their operational effectiveness. The constant threat of acoustic surveillance forced German submarine commanders to adopt ultra-conservative tactics that reduced their ability to attack Allied shipping. U-boat patrol durations, previously limited primarily by fuel capacity and torpedo loads, became constrained by the psychological stress of continuous surveillance. Submarine crews, aware that their movements were being monitored by invisible enemies, experienced fatigue rates that forced premature return to base. German submarine operational capacity decreased not only through direct losses, but through reduced patrol effectiveness caused by acoustic tracking pressure. The cascade effects rippled through German submarine training programs as experienced commanders were lost faster than replacements could be trained. New submarine commanders, lacking the experience of their predecessors, proved even more vulnerable to acoustic tracking due to their tendency to follow predictable tactical patterns that sonobuoy operators could anticipate and counter. The expertise that had made German submarine operations so effective was being systematically eliminated by technology that turned experience into liability. Kapitänleutnant Friedrich Weber's U-731, sunk after 2 hours of continuous acoustic tracking, represented the type of experienced submarine that German forces could least afford to lose. Weber had commanded submarine patrols since 1940, participated in successful wolf pack attacks against multiple convoys, and trained dozens of junior officers in submarine tactics. His destruction by forces guided by sonobuoy intelligence eliminated not only his submarine, but years of tactical knowledge that couldn't be replaced. The technical sophistication of acoustic analysis continued advancing throughout the winter of 1943, as operators gained experience with submarine sound signatures. Dr. Chen's team developed acoustic libraries containing detailed sound profiles for each German submarine class, individual boat identification based on engine harmonics, and predictive algorithms that could anticipate evasive maneuvers based on acoustic patterns. This database enabled operators to identify specific submarines, track their previous encounters, and develop targeted tactics for individual boats. The psychological intelligence gathered through acoustic surveillance provided insights into German submarine operations that conventional intelligence methods couldn't achieve. Sonobuoy operators could determine submarine morale levels from internal noise patterns, estimate crew fatigue from engine operation consistency, and assess combat readiness from torpedo loading activities. This information, combined with traditional intelligence sources, created comprehensive understanding of German submarine capabilities that exceeded anything available to previous anti-submarine efforts. Commander Patricia Wells, analyzing acoustic data at the Underwater Sound Laboratory, identified patterns in German submarine behavior that revealed operational doctrine, tactical preferences, and strategic priorities. Her analysis showed that German commanders were adapting their tactics in response to perceived threats, but their adaptations were based on incorrect assumptions about Allied capabilities. German submarines were becoming more vulnerable while believing they were becoming more secure. The strategic implications of acoustic tracking extended beyond the immediate tactical advantages to fundamental alteration of naval warfare principles. Submarines, which had dominated ocean warfare through stealth and surprise, found their primary advantages negated by technology that made concealment impossible. The revolution in detection capability was as significant as the introduction of radar to air warfare or sonar to surface anti-submarine operations. German submarine doctrine, developed through successful operations against Allied shipping, became counterproductive when applied against forces equipped with acoustic surveillance. Tactics that had proven effective against surface ships and conventional aircraft detection methods actually increased vulnerability to sonobuoy tracking by creating predictable acoustic patterns that experienced operators could anticipate and counter. The manufacturing statistics for sonobuoy production during the first quarter of 1944 demonstrated the scale of industrial commitment to acoustic anti-submarine warfare. American factories produced over 25,000 acoustic sensors. British facilities contributed an additional 8,000 devices, and Canadian production added 3,000 specialized cold weather sonobuoys designed for Arctic operations. This production volume enabled aircraft to deploy acoustic surveillance on a scale that made submarine concealment virtually impossible across vast areas of ocean. Each sonobuoy represented not only immediate tactical capability, but also technological advancement that would influence electronics development, communications technology, and detection systems for decades following the war. The investment in acoustic anti-submarine warfare created technological foundations that extended far beyond immediate military applications. The cumulative effect of sustained sonobuoy operations began manifesting in German submarine effectiveness statistics by early 1944. Average patrol durations decreased as submarines were forced to return to base prematurely. Successful attacks per patrol dropped as submarines spent more time evading detection than hunting targets. Most significantly, submarine survival rates plummeted as acoustic tracking enabled Allied forces to locate and destroy U-boats with unprecedented efficiency. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.